Hi, it's a pleasure to keep going with this series of lectures, and this one will be the first one on atom probe reconstruction. And again, some of the bits here have been taken from previous lectures, including some from François, but mostly from others and myself. Given those lectures a few times now. Before you start going through everything, I just want to remind you that some of the knowledge from these lectures comes from textbooks, and then you might be wanting to go back to some of those. It can be quite interesting sometimes. Okay, so reminding you of the system that we have. So we have a specimen with a radius of curvature below 100 nanometers, cooled down. We apply the voltage. Voltage transforms the surface atoms into ions, pushes them away. We get the ions to fly and go through the counter electrode, which is positioned about 40 microns away. We collect them onto a position sensitive detector. We do the time-of-flight mass spectrometry using laser pulses or high voltage pulses to trigger the departure of the ions. And we can use the information that we get to build this elemental map in 3 dimensions with sub-nanometer resolution. And today we're going to talk about the magic that is involved in between getting these ions and building this 3-dimensional reconstruction. Some preliminaries. So why this lecture? What we have is this series of detector coordinates, the timing of the pulses, time of flight if you want, the voltage that we apply, and the sequence in which we detect the ions. And what we want is to build this XYZ mass or mass to charge ratio. And how do we get to do this? So just to remind you once again, we have this sharp needle with a radius of curvature r, a certain shank angle. We can assume tangential continuity between the shank and the cap. It's not always true, it's typically not true, but that's how the model was initially built. At the high voltage, again, see the previous lectures, and this position sensitive detector, which again has been covered in a previous lecture. One thing that is quite important is that the tip is made of atoms. The specimen contains a whole bunch of atoms arranged on a specific way, typically on a crystalline lattice. So what we need to know is what is the trajectory of the ion from the vicinity of the surface onto the position sensitive detector. Does it follow a straight line like this, or does it have a more complex trajectory? The information we have is just the endpoint. So how can we backtrack this onto the surface of the needle? So let's go back to a little bit of electrostatics. If we consider a sphere of radius r charged to a voltage V, so it's positively charged, the distribution of the electrostatic potential in space will maintain the spherical shapes, and we know how the potential is distributed, how the field actually gets distributed, and we can calculate the trajectory of the ions. Effectively, in that case, the ions will propagate along these straight lines, which are emitted radially from the center of the sphere. And then we can collect them onto a detector. The thing is, if we use Gauss's law, it's really quite simple to write what the field is like, what the potential is like, and the field at the surface is going to be the voltage that we apply divided by the radius of the sphere. If we look at a more realistic geometry for a needle-shaped specimen, we don't really have a sphere. We have a spherical cap sitting on a truncated cone. The distribution of the potential is not exactly as straightforward, but it can be calculated, estimated fairly accurately. And so if we look at the distribution of the potential in a more realistic system with the counter electrode not far from the needle, this is what the potential will look like. And so to model this, the fact that we don't have exactly a sphere, what we typically do is that we assume that it's the voltage divided by the radius, and then we add here, divide this field by a certain factor, which is the field enhancement or field reduction, more accurately, field reduction factor, KF, which varies from typically 2 to 5, is dependent on the specimen's geometry, the distance between the specimen and the counter electrode, and so on and so forth. So again, if we go back to this, more realistic distribution of the potential, the ions will travel, again, either following a straight line like this or a more complex trajectory. We still don't really know, but we can determine it a bit more accurately. The fact is that the ion trajectories get curved. They don't really follow straight lines, and this is because of the distribution of the potential. If you want, the shank here is also positively charged, so it's repelling the ions towards the specimen main axis there. And so we can consider that the ions are projected from this surface onto the detector, and by knowing the impact position, we should be able to backtrack where they come from the specimen surface. So we don't really need to know the precise trajectory. What we need to know is how we can reverse project an impact position onto the specimen surface. Going back to field ion macroscopy, there's been quite a lot of studies of this, and a couple of projections have been studied in more details. This D equal K theta projection, which is an azimuthal equidistant projection, which is basically a straight a proportionality between the distance between 2 points on the detector and the emitting angle. Or, and this is the more prevalent projection, assuming that all of the trajectories are actually straight lines that all cross at a certain projection point that is located along the specimen axis away from the center of the spherical cap. And this, if P is exactly at this position at twice the radius, it would be a stereographic projection. But for us, we're going to use something that is quasi-stereographic, the projection point being not exactly at twice the radius from the apex, but somewhere in between O and that position. And so this distance is the so-called image compression factor, the ICF. Both projection for a limited angular field of view work okay, but actually the quasi-stereographic projection is divergent at higher angles, and the azimuthal equidistant projection works a bit better when we look at wide field of view atom probe data, typically what we get on the LEAP. So there will be some distortions introduced by the fact that the projection model that we use is not really as accurate as it should be. How come we can use this? We can use this because the trajectory of the ions can be fully calculated in principle. We can use this for all of the different masses and all of the different charges, because when Smith and Wells, a bit more than 40 years ago, derived the analytical expression for the distribution of the potential and hence the field, and calculated the trajectories associated to this field distribution, they could actually show that the potential distribution and the trajectories do not depend on the mass, on the charge, or the voltage, assuming that the ions leave with no initial velocity, which we can assume to be true because the transition from atoms to ions happens right at the specimen surface. So if we take all of this into account, we can build a fairly simple model for the reconstruction. That was done in the early 90s. We can assume that the ions will fly along a straight line, that all of the trajectories will cross at a given point that is unique along the specimen axis, position away from the center of the spherical cap along the line there, at a distance which is this image compression factor times the radius. And the projection, is magnified by a factor m, which is basically the flight distance divided by this image compression factor times the radius. This is very simple geometry. And we can typically use ICFs that is between 1 and 2, typically 1.5 to 1.7. And this would be very dependent on the specimen. And I'll get back to this at a later stage. So how do we use this information to build a reconstruction? So we have now an idea of how the atoms are projected from a needle-shaped specimen onto the detector. So we can just build a reconstruction, see where we go. I'm going to give you practically how this is done in the next slides, bearing in mind that this is slightly simplified compared to what you have in the commercial software that you're mostly using, but it's really not that different. And it might appear too simplistic in a way, but actually it is very simplistic. And so don't make a fuss about the way the reconstruction is done. At the moment, it's really, really, really too simplistic. And there are a lot of assumptions that might not always apply to your specific case. All right, so we have XD, YD, and we assume that we know the projection law. So we're going to reverse project XD and YD onto a virtual emitting surface. We can use this magnification factor, the flight distance divided by the ICF times the radius. On a straight flight path instrument, it's quite straightforward. It's just the distance between the specimen and the detector. There's a few more complexities there, which we can go back to at a later stage. ICF, again, it's rather straightforward. I've just explained to you where it comes from. It may not be always that simple because it can vary, for example, during the analysis. It will vary from specimen to specimen. And the radius of curvature is one of the things that we need to somehow estimate. And then we need to make an assumption on what the specimen actually looks like. So that's a typical specimen again, tangential continuity, a certain Schenck angle, a certain radius of the spherical cap, and we only detect a fraction of this spherical cap that is emitting ions. All of this was already described about 40 years ago in this paper from Didier Blavet. I think the paper is in English, but if you can always practice your French. So if we had a no ion compression and the center of the projection was at the center of the spherical cap, we would have a radial projection like this. But actually, the quasi-stereographic projection means that the ions will be coming onto the detector here with some level of compression of the trajectories. So that's what the ICF means. We can actually measure the ICF when you know what is the actual angle between two features. So for example, two sets of atomic plates. We can and measure the distance between their images on the detector. We can actually calculate the ICF, and I will detail this in the next lecture. But basically, the ICF is the ratio of the real angle to the observed angle. So it's always above 1, and it's typically in the range of 1.5. So what about the radius? How can we determine the evolution of the radius as the specimen gets analyzed? There are a couple of ways. First, we can use the voltage. As we've said before, the field that we have is the voltage divided by the radius, with this Kf here that is coming into play. So why not use this to our advantage? We can assume that we know the field, we know Kf, and we measure the voltage. We bias the specimen to a known voltage. So in principle, we can determine the radius of curvature. And so this is, for example, the measurement of the voltage as we analyze a specimen. And we've talked about this in previous lectures, right? So we are applying the voltage so as to maintain a certain detection flux. So we can assume that somehow the field is maintained constant, And so measuring the voltage as we collect ions is a reflection of the fact that the specimen is getting blunter and blunter over time. So KF is quite important. There are ways to measure it. Again, get back to this in the next lecture. But basically, it's one of the parameters that we can change during the reconstruction. But it links the radius to the voltage. And the model that is typically used is for a constant product of KF times F. And it's not always true from specimen to specimen, but also for a single material, but also over the course of a single experiment. Can discuss this in more details later. The other alternative is to use a constant Schenck angle, for example. And then there is a direct relationship. Every time you detect an ion, you go in depth, you can recalculate the new radius of curvature, assuming a certain Schenck angle. In IVAS, there are also a number of options to use, like the tip shape and that types of things. And there are a number of assumptions made there, which I'm not going to detail in this lecture. But basically, all it's doing is do an interpolation of a series of imposed values of the radius. But these are the 2 or 3 different ways to to deduce the radius based on evidence that we have. There are many discussions that we can have regarding the validity of a specific model with respect to another one. And I just want you to have views that these are just assumptions, they are not real. But we still have some indications that they're not all completely bogus. So when we use the voltage, for example, if we took 2 specimens with more or less the same Schenck angle, we can see that the evolution of the voltage follows more or less the same trend, the same slope. So this seems to work okay. And the same thing here, same radius, but 2 different Schenck angles, and we can see that the evolution of the radius as a function of ion sequence or depth is quite different. And so the radius gives you really the field, and the Schenck angle imposes an evolution of the radius, basically, and hence the evolution of the voltage, the slope. Okay, so now we've talked about how to get to the parameters that gives us the magnification. So how to go from the lateral positions on the detector onto the specimen surface. And here, what we need to discuss is how to get to the 3rd dimension. So how do we build the depth? I'm going to go through the way it was done and described in Ba's paper from the early 90s. Things have changed a little bit, and I will also discuss that briefly. But these are just small adjustments on a specific concept, and ultimately nothing has been revolutionized in any way in the way the reconstruction is made. So if you read the 1995 paper from Pascal Ba and Didier Blavet and Alain Bostel, you'll see that the concept is really quite straightforward. So if we assume that we have a virtual emitting surface from which the ion that was detected originates, we can assume that every time we are going to process one of the ions, it comes from a slightly different depth. And that depth is basically moved down every time we process one ion. And so we can recalculate this evolution of the depth, and that's what we're going to discuss in the next few slides. And for each detected ion, we move this emitting surface down a little bit, and a little bit. Okay? And then we have to assume that the emitting surface is curved, so we will have to account for this. And the curvature is dependent on whatever evolution of the radius you've decided to use, whether the voltage or the Schenck angle or the tip profile. So how much do we need to move down this emitting surface? What we actually know is that we are detecting a certain number of ions, and this number of ions will make up a certain volume, right? And so we've detected N ions, for example. We know that we're not detecting all of the ions because of the detection efficiency that is limited. And we can just sum up the number of ions times the volume that these atoms occupy inside of the specimen initially. So what we know is the total volume. And so based on this, we can infer that if we know the analyzed area at the start and at the end, because we know the magnification and we know the area of the detector, we can deduce the analyzed from the analyzed volume the total depth that we've analyzed. And the math is really quite straightforward to do. And this will give us an idea of how much we need to move down in Z every time we process one ion. So what we are basically saying is that every time we process one ion, it's like we're taking the atomic volume of that one specific ion and distribute it over the entire analyzed area. And that gives us a dz that is quite tiny, but it's there, and then we just add it up progressively. So this is the way to look at it. We have atoms sitting on the surface, and they will be ionized and detected in a certain sequence. So from first atom, second, third, fourth, fifth, sixth, so on and so forth. So we are detecting them, and every time we collect one of these ions, we move the emitting surface down by a tiny amount. And then what we need to do is move these atoms down just a little bit to account for the curvature of the surface. And this is the way it was done initially in Base protocol, is just to move them down by a tiny little bit, which is proportional to the radius of curvature and the distance between the center and the impact position, the reconstructed position, sorry. And this is what gives us finally the final positions that have been reconstructed. It's as simple as this. These have limitations because the way it's being done right now in Base protocol is just to move the atoms down along Z and not in XY as well. So this is not really accurate, or it was not really accurate at the time. The magnification, we assume it to be constant all across the field of view, which is not really right. And in a point projection, it actually doesn't really work. We have to assume that we know the analyzed area and that it's sort of flat like this at the end of the needle, which is not really true. So all of these assumptions were okay when the field of view of the atom probe that was the angular field of view of the atom probe was very tiny, just a few degrees off the main axis. But for wide field of view atom probes like the LEAP, it doesn't really work anymore. So there have been a few changes made by Imago and Kameka now to try and make this slightly better. So for example, when you look at the protocol that was described by Geiser et al., Brian Geiser being the person who developed all of these algorithms at Kameka, and all of these are described in quite a lot of details in their handbook of the local electrode atom probe. So I invite you to read this in detail. So basically, if you assume this shank angle reconstruction model, we can use some of the work by Walk. It's not really visible here, but I can send you the reference if you want, to give a slightly better estimation of the analyzed volume by considering that it's not just a cylinder, but has a spherical cap at the top, at the bottom, and this cylindrical region or truncated cone region in the center. So we can get slightly better reconstructions by assuming the different contributions of the caps and of the truncated cone. But to do this properly, you need to have a value of this shank angle, for example, which we don't really always know, and especially because it might not be the one that we image easily with electron microscopy. But anyway, these works quite okay. We can still do some fairly good reconstructions, but it's very, very, very simple. So just to summarize, we model the specimen geometry as a spherical cap on a truncated cone. The spherical cap has a certain radius. The radius we can determine from the voltage or the shank angle, assuming a certain geometry, either through a shank angle reconstruction or by imposing an evolution of the radius through the T profile, for example. And as each line is processed, we reconstruct this as an atom onto this virtual emitting surface. So we just reverse project this position onto the spherical cap. And then we move the spherical cap down by just a tiny amount, which is proportional to the atomic volume and inversely proportional to the analyzed surface. And we do this sequentially. So the sequence in which we detect the ions is used to build the depth. So these different models just have a number of parameters that need to be defined. So the image compression factor, the field itself, the atomic volume, which has to be not the atomic volume or the ionic volume, but the volume of an atom inside of the material initially. So it has to account for the free volume, so will depend on the crystal structure, for example, which for AP Suite or IVAS never took into account, for example. So there are quite a lot of assumptions in this in the reconstruction, in the way it's been implemented, that need to be borne in mind. And if you just don't want to use the voltage curve to get the radius, but use the shank angle because it might look better, there's still quite a lot of assumptions in there with respect to the radius and the shank angle that you're going to be using, and same thing for the tip profile reconstruction. You're imposing a radius which might not actually be right, in part because during the field evaporation process the specimen itself will change shape, and when you go from one phase to another locally radii will develop, and none of these things are taken into account in the current reconstruction protocol. So on this, I'm going to conclude the current lecture. There will be another one on reconstruction with some more details on what to do and how to deal with it, and some problems and limitations. Thanks for your attention.